that we covered last time. And I just want to make a couple points about all this because it's kind of interesting. Here we have the system with two parallel components, and it's sort of like a circuit in that if either of these two things is functional, it will complete a path from A to B. If both of them are, that's overkill, but if the system will only break if all the components are broken. Okay, and maybe building a system like this seems a little weird to you. It might be a little bit weird, because you would never really rely on something that will work 50% of the time, like on a coin flip. I mean, maybe if that's your best option, that's what you do, right? And if we look at the case where P is a half, right, this is essentially a coin flip, you would probably not rely on one coin flip for your system to be reliable, right? And you might not even be happy with two coin flips, right? You have to lose both the coin flips to lose, and that's 25%, right? And that doesn't feel very good for, robustness. Okay, so if P is equal to a half, relying on one or two components might not be the most reliable. So the solution is take as many components as will make you feel comfortable. Okay, and your textbooks suggest not just using two components or three components. They suggest a really large K. Okay, so they when they get to the this algorithm here, the one that we focused on, primality testing, they suggested having K something around 200. So you try 200 primality tests, and if K is say 200, then the chance of failure is 2 to the minus 200. Okay, because all of them have to break at the same time. Now, just to give you an idea of what 2 to the minus 200 means, 2 to the 10 is around 1,000, right? It's 1024. So that gives you 3 decimal zeros. So 2 to the 200 should give you, let's see, 22 to the 10s, basically. So that'll give you 60 zeros. Okay, so this is around 10 to the minus 60. And you did the lottery problem on assignment 1, or everyone had to do that one, right? You had to do the lottery problem. So the chances of you winning the Lotto Supermax on a single line of numbers is 1 in 100 million. Okay, so that's 10 to the minus 8, right? So this is 10 to the 52 times less likely, and they sort of list a whole bunch of, your textbooks are great about being very dramatic, the chances of a meteor hitting and destroying the Earth. Okay, so any second would be around 10 to the minus 60. Okay, so really, really super unlikely events occur at this level, and chances are you will not encounter any failure at this level of probability in your lifetime, in the universe's lifetime, for that matter. Okay, so this is an interesting sort of approach that maybe you hadn't thought of, because you want to have some certainty. There is no certainty in this algorithm, but it's still pretty cool that just by spot checking, okay, by sampling a whole bunch of things, looking for witnesses, if you search for 200 witnesses, you get the same level of probability of error. This is a one-sided error, by the way, okay, because if any of these witnesses happens to turn up good, it will 100% tell you that it's composite. So it will never return a it will never get no wrong. It will never get no wrong. Okay, so it will never get no wrong, but it will sometimes get yes wrong. And this is what's known as a one-sided error. Okay, but still, this is the industrial strength algorithm for finding primes that is used today. Okay, so pick a random string of bits that's odd and run is prime. And if it's not prime, then try another one, and try another one until you trip over one. And there's enough prime numbers, there's enough density of prime numbers that you will trip over one in not too long a time. Okay, we have 2 more lectures on independence. There's actually not a lot of technical stuff to cover. I'm going to give you the other set of definitions today. And then on Friday, we're going to look at another algorithm that does this sort of probability amplification. It's another Monte Carlo algorithm for not verifying polynomial multiplication, which was one of the applications I suggested earlier, but matrix multiplication, which is a very expensive algorithm to implement in computer science. Okay, but that's for Friday. All right. We talked about A being independent of B. A is a definition for that. Maybe you like the conditional probability definition. Maybe you like the multiplying of the two things definition. Either way, it's all fine. What if you have 3 events or 4 events? Can you have independence there? Sure. Okay, here's the definition. So if you have K events, they are independent if, and only if, for every subset of the numbers 1 through K. Okay, so these are the numbers 1 through K. And notice that the indices here on the sets are numbered 1 through K. Okay, so these things have to match. The intersection of any of those sets will equal the products of their individual probabilities. Okay, so just to show you what's going on here, first of all, what is C? Okay, so C, or this C, whatever you want. This is known as an index set. And why is it called an index set? Well, it's an index set because it's collecting, these numbers here are collecting all the indices of the sets that are being intersected, or probabilities that are being multiplied. So you'll look at the notation here. It's intersecting over for all I in C. Okay, so if we look at the list that's over here of all the possible C's, okay, so for, this is like, this is C is equal to 1, 2. Okay, so that's one possible subset, and this is 1, 3, and this is 1, 4, right? So we're taking all i's in C, iterating all over i's in C, and intersecting them together, and here we're multiplying all the individual probabilities again for all the i's in C. Okay, so all it's doing is collecting all the possible indices in here. 2, 3, 2, 4. Here's some 3s, say 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, and here's all 4. Okay, we don't include the intersects of 0 and 1 thing because it's trivial. Of course, the probability of A1 equals the probability of A1. Okay, so it's pretty easy. Okay, so if all possible things, all possible subsets or collections of these sets give you this product of probabilities, then the collection of k-sets are said to be independent. Okay, so a couple of notes. First, it is not just sufficient to check that the intersection of all k-sets equals the probability of them individually all multiplied together. Okay, so for instance, this line down here. Okay, so it's not just sufficient to check this out. You can find counterexamples where this happens to be true, but you don't have even intersections of two things. Okay, like A1 and A2 are independent. Okay, so it's possible that this be true and A1 and A2 be not independent. So you have to check everything. Okay, and this is a very exhaustive list for 4 sets, right? How many things have we got here? We got 6 up here. Those are all the, I guess, 4 choose 2 single intersects, and then we have 4 choose 3. There's 4 double intersects, and then we have 1 triple intersects. That's 11 things you have to do. Okay, and generally this thing grows exponentially. So it's actually a lot of work to do. Okay, and it's not just this last line down here. Okay, furthermore, it's not sufficient just to check each individual set of pairs. Okay, if you do that, you're doing something else. Okay, so these are all the pairs up here. Okay, if you check all the pairs are independent of each other, this is known as pairwise independence. So each pair that you pick will give you independence. But it does not imply that you'll end up getting intersections of 3 things or 4 things. Okay, so this is not the same thing as checking everything. Mutual independence. Okay, mutual independence is this whole table. Okay, so that's mutual independence. Mutual independence is very strong, right? There's a lot of things to verify, and it certainly implies pairwise independence. Okay, so but it's a lot more to do, and oftentimes you don't have to do it all. Okay, so you're going to see in the coming units. It's usually good enough for our purposes, like when we're talking about expected value. We're going to do that maybe in a few weeks, and variance as well. Those things only require pairwise independence, okay, which is a lot easier to do, right? You only have to do this much work, only an n squared amount of work as opposed to a 2 to the n amount of work. Okay, it's a lot easier to verify. Okay, so just keep this in mind that the 2 things are different. Mutual independence does imply pairwise independence, but pairwise independence does not necessarily imply mutual independence. And I may ask you some questions on a coming piece of homework for you to find counterexamples where you might have this sort of thing. Pairwise doesn't imply mutual. Actually, I think our next example does that, or something like this, where you have the intersection of all the sets gets you this product, but they're not independent pairwise. Okay, so that's the definition of the day. And as an example of this, let's look at coin flipping. Okay, so we flip 3 coins. Let's number them 1, 2, and 3. Okay, so the first coin comes up heads or tails, second coin comes up heads or tails, third coin comes up heads and tails. And we have 3 events, A, B, and C. Okay, event A talks about the first 2 coins. If the first 2 coins have the same outcome, then it's in event A. B is coins 1 and 3 having the same outcome, and C is the last 2 coins, okay, coins 2 and 3. Are they independent? Okay, so 3 events. So we need to verify, okay, so all the pairwise ones, okay, that each A, B, or BC or AC are independent. And for mutual independence, we need one more. We need that A intersect B intersect C, that probability equals the product of probabilities A, B, and C. So let's do it. Okay, so what's in A? Well, there are 8 total outcomes. And A is the first 2 coins have the same outcome. Okay, so that could be all heads. It could be heads, heads, tails. And I think that's the only ones where the heads are the first 2. And it could be tails, tails, heads, or tails, tails, tails. B is similar, okay, except the first and third have to match. So if we're doing something similar, like we have H and H, these things match, then the middle coin can be a heads or a tails, or the middle coin can be a heads or a tails. C is going to have something similar. The last two coins have the same outcome, so that'll be something heads heads and something tails tails. Okay, two possibilities for each: heads, tails, heads, tails. It'll give you a moment to catch up. Okay, 8 different outcomes in total. 8 for 3 coins, 2 to the 3. Probability of each of these is equal. Okay, so probability of A equals the probability of B equals the probability of C equals a half. Okay, now we're going to intersect them. And let's look at the common elements. The common elements, well, heads, 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 and tails, tails, tails seem to be common to all 3. If you look at the middle ones, there's actually no overlap among any of them. Okay, so all 6 of these things are unique. Okay, that's good, right? Because the A intersect B, A intersect C, B intersect C, they're all the same, right? They all have HHH and TTT in it. Okay, so if we want the probability of A intersects C, it's going to be the same as all the single intersects. It's going to be the probability of those same 2 outcomes. And of course, 2 out of 8 gives us a quarter. And a quarter is good, right? Because, we're going to be taking the product of a pair of these things, okay? And a half times a half is a quarter. That's really good news, right? So this, I'll just put a check mark there. I don't want to write too much, but this bit here, this is pairwise independence, okay? All 3 of them, okay? So if you pick any 2 of them, they will be independent of each other. And I know that seems a little bit strange because they seem to be entangled. They seem to have a coin in common, okay? But it actually works out. But yeah, math works out. It's a quarter of the time they will both be true. Okay, so we got pairwise independence. What about mutual independence? Okay, well, mutual independence means that we want to verify the 2 intersect case. We're going to check the probability of A intersect B intersect C. Okay, and we want to check that equals the product of probability of A, probability of B, times the probability of C. Okay, what's the probability of A intersect B intersect C? It's the product of, yep. 1/4, why? Yeah, all 3 of these have the same 3 items here, yeah. Okay, so this is a quarter, right? 2 out of the 8 outcomes. And over here, it's a half times a half times a half, which is an eighth. Okay, and a quarter is not equal to an eighth. Okay, so this is a case where you have a collection of outcomes, sorry, a collection of events, pardon me, that are pairwise independent, but not mutually independent. Good. Pause here for a moment. Any questions about the definition or this example? So you're trying to assign some intuitiveness to 3 things being mutually independent. Yeah. So I guess the effect of 2 of them happening does not affect the impact of the third. I guess is the thing. And indeed, if 2 of these things do happen, it does impact the third, right? Yeah. Yeah. I think that's my intuition anyway. Yeah. Thanks for that. Other questions? Yeah. Okay, here's the plan for the rest of today. All right, we are going to skip the serial one, okay, serial components, because it's a really fast example, and it's not too fast, but it's easier for us to fit it in on Friday, and I want to make sure we get through a longer example that we might not have time for if we leave it until the end, okay? So we're going to do this, we'll do the summary slide, and then we'll do the 5 dice, and hopefully that'll take us to time, okay? So skip that. Okay, so here are some things for you to ponder. Okay, first one, and I think what we'll do, because, you know, voting is fun, you're each going to vote on these two things, okay? So the first question for you. If A is independent of B, then is B independent of A? Prepare to vote. You ready? Is it voting time? You're not ready, are you? Okay, a little bit more time. All right, let's do it. All right, if A is independent of B, then is B independent of A? Who thinks this is true in general? Who thinks it's false? Okay, about a 50-50 split. Let's hear from the true camp. Why do you think this is true? How would you justify it if I asked you to justify or prove your answer? What would you do? Good. Yeah, there's a little bit of symmetry in the way that independence is stated, at least the second definition. Okay, in that P, maybe I'll just write it down. All right. So if you have probability of A intersect B equals the probability of A times the probability of B, there's nothing tied to the order of this, right? So, you know, you can flop the A and B due to commutativity, and you can flop this multiplication because multiplication is commutative as well, right? Okay, so yes, by the commutativity of things, either multiplication or intersect. What if A is the universe? So what happens to you? Why not? So, I mean, if you look at the equation, okay, so let's just imagine A was the universe. Okay, so universe intersect B is B, and probability of universe is 1. So that gives you 1 times probability of B. So it seems to work out. Let's just think about it in terms of conditional probability, yeah? So if you wanted to say, so we're saying B condition on A, right? B condition on A. So if you know the probability of B given that the universe occurs, well, the universe is anything. Anything could occur. So you basically have the probability of B back, right? Nothing really happened. And the opposite will occur as well. The probability that the universe occurred, given that B occurred, I mean, the probability the universe occurred was 1, right? And it stays 1, even though you know B occurred, right? So I think it works out okay. Same thing if they're null sets. Thanks for the question. That's a good question. I like thinking about those edge cases, and they come up from time to time. I think your present assignment has some of those cases in it, right? Where you're dealing with conditioning on the universe. Yeah, it's good to think about those. If you like to think about conditioning, I do have another version of this. Okay, so if you know the probability of A given B is the probability of A, and you're asked to prove the opposite, right? You want to show that B is independent of A. You would show that the probability of B given A, you want to show that that is equal to the probability of B. You would use Bayes' theorem, right? Because if you know the probability of A given B, you want to flop those things. That's how you would go about it in Bayes' theorem, right? So then you'd say, okay, then by Bayes' theorem, the probability of B given A is equal to the probability of A given B times the, well, I guess it's just the ratio of the probability of B divided by A. And, you know, we have an equality up here, and so those two things will divide away, and you get what you want. You get a probability of B. Yeah? Okay. Next part. If A and B are independent, then are A and B complement independent? Okay, so think about this. So in terms of the Venn diagram, okay, so B complement is all this space that overlaps A or whatever, whatever B didn't overlap, and it has a certain portion that it didn't overlap as well. Okay, that A doesn't overlap. Okay, so think about this for a moment and prepare to vote. Okay, you ready? No, you're not ready. All right, a little more time. Okay, you look more ready. Let's vote. If A and B are independent, then are A and B complement independent? Who thinks this is true in general? About 10 of you. Who thinks this is false in general? And there's some counterexamples. Okay, more of you. Okay, well, this is true. Which seems really weird in a way. It feels like the math shouldn't work out. But, I don't know, I drew this geometrically. And if you look at, this is just intuitively, this is by picture, Okay, so if you know what independence means in terms of Bayes' theorem, or if not Bayes' theorem, the condition probability thing, this blue bit is the fraction of A that survives when you condition on B, and it should be the same fraction overall as the original rectangle. So whatever's left over, whatever's in the white or gray region up here that overlaps B bar, should be in the same proportion. And maybe you don't believe that. It's a proof by picture. Let me work at it from another angle. If I was to tell you that A was independent of B, okay, in other words, A, condition on B, okay, the probability doesn't change, the probability is the same. You would say that B doesn't matter, right? B doesn't matter, whether the fact that B occurred doesn't matter to the probability. So does the probability matter that when B doesn't occur? It's the same thing, right? It either does occur or doesn't occur. It shouldn't affect the probability of A. Okay, that's my intuition, and maybe you like that or maybe you don't. But here's some algebra, and we're going to do this together. Okay, poof. We would like to show the probability of A intersect B bar eventually equals probability of A times the probability of B bar. I'm going to do the first step, and you're going to do the rest. I'm counting on you. This is equal to the probability of A minus B, because A intersect B bar equals A minus B. And I'm going to give you a hint for the first step. There is a rule that you can use from our probability rules for the probability of A minus B. What does the probability of A minus B equal? Probability of... Or you just gave me this back. That's not much fun. Sorry. Minus the probability of A intersection B. But yep, you got it. Okay, so this is the difference rule. Okay, if we got here, what would you do next? Speak loudly. Oh boy. Well, at least you said it loudly. Never mind. All right. Yeah, you. Good. Why? Good. A and B are independent, so you can use that fact here. Now what? What's going on? Yep, factor. Good. Okay, so there's a common factor of probability of A to pull out here. And then? Sorry, yep. Guy in front. It's not a definition, there's a rule. What's the rule? You're right. Good instinct. There's a rule for this. What's the name of the rule? Complement rule. Okay, and likewise, you can do this again, and you can show that A bar is independent of B bar, and it's also independent of B. Okay, so if you have A is independent of B, you get all of them. Okay, two rules. A little surprising to some of you, and maybe a little bit surprising for me to see about half the room thought this wasn't true. I thought that would be a little bit more straightforward, and this one might be a surprise to most of you, maybe for good reason. It doesn't really seem like it should be, but it is. Okay, questions? All right, summary time. Okay, and besides a few definitions, there's not a lot of work to be done in this unit. There's a lot of algorithms, okay, and we'll do the other one on Friday, but let's do the definitions. Okay, A and B are independent if the probability of A intersect B equals the product of their two individual probabilities, or when A, if B, that probability doesn't change, okay, so it's equal to the probability of A. Otherwise, they are dependent. Okay, you can have larger sets of events, and if any pair of them are independent, every single pair, they're called pairwise independent. And if all the triples and all the quadruples and all the subsets of indices from those K sets, any permutation you take follows the independence rule, they're called mutually independent. Mutually independent is, again, it's much stronger than pairwise independence. Most of the time, we're just going to do pairwise. We're not going to need mutual independence for most applications going forward, but in one or two instances, you might see it. Okay, so just so that you're aware. Okay, last problem, and then we'll call it a day. 5 dice. You roll 5 fair dice, nothing complicated. 6-sided dice. What's the probability their sum is evenly divisible by 6? There's a problem that was posed in O'Donnell, and they go through an analysis there. I'm going to do their analysis. And this is an interesting problem in that, the event space is non-trivial. Okay, you can have anywhere between a total of 5 and 30 as your outcomes. And besides it being symmetric, the probabilities are not obvious what each outcome will give you. Okay, the reason we're doing this problem is not to torture you, but we need this result, we need this technique anyway, to do what we need to do on Friday. Okay, so normally I would parcel this with the stuff on Friday, and indeed it's adjacent to that material, but if I leave it till Friday, we're going to run out of time. Okay, so we're going to do it today. I'll let it sit with you, and then on Friday I'm going to reference this, and hopefully we'll be prepared. Okay. All right. To do this, we're going to require 2 tricks. Okay. First of all, I just want to say that any sort of obvious try everything solution is going to encounter some headwind. You won't want to try all the cases. Okay. Let A be the event. The 5 dice sum to a multiple of 6. You could draw a probability tree. It's a very massive probability tree. Or maybe do some sort of computer simulation, or somehow you're cleverer than I am and you're able to enumerate all 6 to the 5 outcomes. There's a lot of outcomes, just saying. Okay. But there's a trick. Actually, 2 tricks. Okay, and this is the trick that we're going to need on Friday, okay, for another thing that has to do with computer science. But we're going to do it for dice today, okay, and the answer is surprising and the tricks are kind of cool. Okay, so here's the first trick. The first trick is to condition on the sum of the first 4 dice. Okay, we're setting the 5th die aside, and we'll add it in a second, I promise. Okay, but we're going to condition on the first 4 dice. Okay, what are the possible outcomes? Well, 4 dice can range anywhere between 4 and 24, right? 4 if it's all 1s, 24 if it's all 6s, and any integer in between. The possible sums: 4, 5, 6, 23, 24. So we're going to define B sub k to be the event, the first 4 dice, total k. Okay, a moment to catch up. I don't know what's up with the microphone today. I apologize for that. Okay, is it still working? Okay, it's a miracle. I used to have this crackling thing with the microphone. I don't know why. It works some days and it doesn't work other days. I don't know if it's part of the receiver thing or if there's a broken wire in between. Anyway, first time it's acted up all turns, so I feel lucky. What's the probability that the thing now? Let's focus on this. All right. Okay, there are 21 events here. And one of these things has to occur. Okay, so, and only one. So each of these B4 through B24 partition the sample space. Then we can use the law of total probability. On these 21 items, 21 events, that it certainly works. Okay, so the probability of A equals the probability of A given B4 times the probability of B4, okay, plus the probability of A given B5 times the probability of B5, and just use the dot, dot, dot. You could use the sigma notation, but it's a little easier to read sometimes. Okay, so far so good. Okay, so we roll the first 4 dice, or at least we sort of set them aside in our head, and we find their total. And it's like in a 21-way if statement. If it's 4, then we multiply by the probability of B4. What it is likely we're going to get 5 dice that are divisible by 6, 5 dice divisible by 6, multiplied by B5. So, okay, so it's a 21-way if statement. Okay, this seems like it's worse than when it started. And maybe it's not so easy to determine what this is, probability B4. That's probably pretty easy, actually. Maybe B5 is pretty easy, too. But, what's the probability of B12, like rolling a total of 12 on 4 dice? I don't know. I don't know how to crack that. Okay, so the second trick, and it's not really a trick, is to resist the temptation to try and find these probabilities. Okay, instead we're going to go after these ones. Okay, and we'll start with that, but we're going to go after all of those. Okay, so the second trick, so I'll underline first trick, second trick, is to resist the temptation to try and evaluate the probability of B4, or probability of BK, any of them. Instead, we ask, what's the probability of A given B4? Okay, so let's read this, what it means. The probability that we can roll a number that is the total that's divisible by 6 on 5 dice, given that the first 4 dice are divisible by, that are equal 4, pardon. Okay, and if you look at the problem, right, the first 4 dice have got 4, and the fifth die can be 1, 2, 3, 4, 5, 6, so the total can be 5, 6, 7, 8, 9, 10. Okay, so if the first 4 dice total 4, then the total, after we add in the fifth die, will be one of 5, 6, 7, 8, 9, or 10, and each of them is equally likely. And if you look at that list of numbers, there are contiguous 6 numbers in a row. One of them is divisible by 6. The other ones are not. Okay, so the probability of A given B4 is 1/6. Okay, so just to recap the argument here, the probability that on 5 dice you get something that's total divisible by 6, given that the first 4 are divisible by 4, equal 4, pardon me, you have to add on one more die to 4. Like it's 5, 6, 7, 8, 9, or 10. Only one of those is divisible by 6. And for any 6 contiguous numbers, exactly one is going to be divisible by 6. So this is going to be the same for probability of A given B5, A given B6, and so on. A given B24. They're all 1/6. Okay, which means that's going to be a 6, that's going to be a 6, that's going to be a 6. They're all a 6. We can factor out a 6th once we sub them in. Okay, so subbing them back in, the probability of A is a 6 times the probability of B4, plus a 6 times the probability of B5, plus a 6 times the probability of B24. So we factor out the 6th. And this, what's that equal to? 1. Why? Yeah, it's partitioning S, right? Okay, so this is a partition